expression or simplify a ceiling expression. Now let's just make sure everybody remembers what we mean by ceiling. This is different from the floor notation. This is just, I guess, squared brackets kind of turned in. I'm not sure what you call it really. But let's say we want to do the ceiling of 9.2. So that's 9.2 right there. Now the floor of this would be 9, but the ceiling is equal to 10, as you may have surmised, and that's very, the purpose of this is just to create a working definition that we can work on use to work on the problem, the blueprint problem. So because 9 is less than 9.2, less than or equal to 10. So you see you have an interval of length 1 there, where the argument can reside. Now notice that the ceiling of 10 would be 10, just like the floor of 10 would be 10. Okay, so this is kind of what you would call a definition right down here. And y'all, of course, C is an integer, okay? C is definitely an integer. We'll just call it Z, right? It's a member of Z, it's an integer. Okay, now we're supposed to simplify the kind of strange instructions, probably the most confusing instructions in mathematics. We're supposed to simplify the ceiling of this binomial, the square root of 3 plus 1 quantity raised to the 2m power, where m is a natural number. Now, the very first, an important thing to write down, which turns out to be super, super useful, is that this expression plus the difference expression is going to be a natural number. All right. And if you take a look at this, the square root of 3 minus 1 is less than 1. The square root of 3 minus 1 is less than 1, which kind of is motivated by the fact that the length of this interval is 1. It's numbers in an interval of length 1. And so that's kind of connected to this choice, really. It's not really that's not the best motivation. But notice that this is true because this is a kind of what they call a classical alternating series where the negative terms cancel out. Now notice right here, this 2 times m, choose odd. This is the binomial, a typical term in this binomial expansion right here with odd exponents. Notice that 2m minus an odd number is an odd number, and then 1 raised to the odd is an odd, right? So this is a typical odd term in this expansion, okay? And again, note that 2m minus an odd number is an odd number. So these are both odd exponents. This is an odd exponent. This is an odd exponent right here, okay? Now, notice that the minus, this would be a typical odd termed exponent term in this expansion, right? But the minus 1 raised to the odd will make this the negative counterpart, or the arithmetic, or the additive inverse of this term right here. So it's all going to equal 0, right? And so that explains why this is an integer. If you also observe that the square root of 3, okay, raised to an even power, all the other terms would have even exponents in these expansions. So the square root of 3 raised to an even power, square root of 3 raised to an even power, okay, is certainly a natural number, folks. And I'm just going to write that it's a member of the natural numbers. All right, so you see that's why this entire expression sums up to some natural number, because all of the odd terms cancel out to give you 0, and all of the even terms are natural numbers. And then, of course, these binomial coefficients here, the binomial coefficients are natural numbers, okay? So this is a big result. Now let's move along. A lot of the work is out of the way right now. Now I just gave it a name, okay? I declared that it was a natural number, but I went ahead and just gave it a name because it's just easier to process. Now again, the square root of 3 minus 1 is less than 1, right? The square root of 4 minus 1 is just 1, so the square root of 3 minus 1 is less than 1, and when you square, when you elevate it to a higher exponent, it's still going to be stuck between 0 and 1, right? Okay, and so that means this, right? That means that k minus 1 is a lower bound for the square root of 3 plus 1, and k is an upper bound, right? But that's exactly what this definition says. That's what we mean by the ceiling, right? And so you see, we see that the answer to our question, it's equal to k. So that would be the ceiling of this expression. Now, of course, that would involve an expansion, but this is literally the answer to the question, and I guess in a closed form, right? Okay, so that would be the solution to the problem. Now, it's not particularly useful because you go, well, okay, that doesn't, but it is a closed form solution for the ceiling of this expression. Now, let's take a look at a concrete example here. Okay, I just chose for m equals 2 right here. Okay, so this is the case. Let me write up here, m equals 2. Okay, m equals 2. And I just hand multiplied it, just use the binomial expansion. Okay, you guys may remember that for 4, the coefficients are 1, 6, 4, 1, 4, 6, 4, 1. Okay, there's a symmetry of these things. But anyway, notice how the negative guys cancel out. The negative odd exponented terms, which are also irrational numbers, all cancel out. See, everything cancels out nicely. Okay, then all that's really left is both of them sum up to 28. And so we can see for this concrete example, m equals 2, the ceiling of this number is actually equal to 56. And again, the ceiling always has to map to an integer. And for the positive numbers, it would be a natural number. Yeah, I like this problem a little bit. It's a little bit of abstract reasoning about the canceling right here, and then the key right here is also noticing. I didn't write that down anywhere, but the square root of 3. Square root of 3 minus 1 is less than 1. Less than 1 for sure. And when you square that, you're still going to get, in other words, that's this statement right here that I kind of penciled through there. Okay. So anyway, I hope you enjoyed it. I liked it a lot. Thanks for viewing.